These are power series and radius of convergence. That's the formation of the power series, but you see that C sub n? I don't want you to think that's just a constant. It means that C sub n can involve a -1 to the n. It could have a monomial in it, like an n cubed. It could have a 3 to the nth in the denominator. So all that I'm putting my hand over would be the C sub n. And then there's this variable x raised to the n. And everything's about the x. We're going to figure out when does this power series converge for different values of x. So it's all about that variable x. There's a lot of letters in there, right? N's and x's. But we're determining it for the variable x. So when they say determine the radius of convergence of this power series here, and the interval convergence, we're talking about the variables x. What numbers for x make this converge? So that's why I'm going to go over here, that x there. I'm just going to change the color. So you know when they're talking about, what are you talking about in terms of the radius of convergence? That's the variable x. What numbers could we substitute for x? 2 or -1/2 or something, and that power series will always converge. So to do this, I think you'll like this section. We're going to do the ratio test repeatedly. That's all we're going to do. So you can make a note with 11.8, we're always going to use the ratio test. So we'll use the ratio test to determine what values of x make it converge in that radius of convergence. So we use the ratio test. We should briefly review that at the beginning. What was that? That's where we had to see the limit as n approached infinity. We did the a sub 1, a sub n plus 1 of this sequence here, the sequence being a part of the series, divided by a sub 1. We took the absolute value, and when did this converge? When this limit was? Great memory, less than 1. That's what we'll be checking. So over and over and over. Let's just leave this up the entire time for section 11.8. We're just going to use the ratio test to determine the variable, the numbers of x that make it converge. Something else comes up in this section you might not have seen since an intermediate algebra class. It's not hard, but something like this at the very end. I'm just going to make this up. Algebraically, do you know how you can write this without those bars? It's not hard. They call this an absolute value inequality. It's taught in an intermediate algebra class. So if you haven't done it, it could have been like years ago. But this can be written as, you put another arrow over here, and you put a -2. So this means x is between -2 and 2. So we'll do that over and over again. I just want to point that out. So, but it might have been a long time since you did this, or you may have never done that. It's taught. That's where it's taught. It's not even like in a college algebra. Well, sometimes you put it in college algebra. Hey, so what would this be? I'll make up another example. What was x minus 1, and this was a 3? So how would you set this up? X minus 1, take the bars off. There's your 3. What goes on that side? And then you solve for the x in the middle, right? Just dealing with the inequality. You want add a 1, add a 1, add a 1. So what do you get for x? What's in between? A 4 and 2. There you go. So that's something we'll do at the very end. When they talk about finding the interval of convergence, it'll be the last step. You'll just go, oh, let me just. But that might have been new to you. I mean, that's where that's taught. You're like, I've never seen that before. They call them absolute value inequalities. So that comes up every problem we do. When it comes down to the end. You go, why? Because there's bars here. See the absolute value bars? And we're going to have that variable x. So those bars are going to go around that x. And that's why this is going to come out in the end every time. Every time you'll have an x with that bar around the end. All right, so this is the first problem we're going to work together. We're going to use the ratio test to determine the radius of convergence. So what we mean by that, what values of x make this series here converge. So let's start out, we'll get working on it. Let's do the ratio test. All right, so I'll use the ratio test. I get the limit. As n approaches infinity, we put the absolute value bars. -1, let's start out. That would be -1 to the n plus 1, so far so good? I want to take this slow. How do you write n cubed? So I replaced n with n plus 1. So is it this, Or is it this? Just to make sure everyone's comfortable with the ratio. It's this one. Oh, good, you got it. I'm gonna put that down. Everyone, very good. That's what we mean. That just stays x to the n. We put x to the n, we put a plus 1, right? So far, so good from substituting n plus 1s in the top. But now I got the what? There's still a what? 3 to the n, so that's 3 to the n plus 1. All right. All right, we're good to go. A sub n plus 1 is complete. Now I got to put this all over what? A long fraction bar. And what's this all over? I just repeat the expression. All right. Negative 1. N cubed. X to the n. All over 3 to the n. Absolute value bars. And when will this converge? I might as well put it over here when this entire limit is less than a 1. So you'll do that on every problem. When you determine the radius of convergence, you're always trying to find out when the limit's less than 1. Not a 0, it's always going to be less than 1. Remember, this test is inconclusive if it equals 1. Hey, to save time, how do you divide fractions? You might do this automatically in every problem. I notice students do this all the time. This took a lot of writing, do you agree? And sometimes when you got to write so much, it can be confusing. I might make a typo or write the wrong expression. So I am just going to put this next to it and flip it, right? I'm just going to take this, put it right here and flip it. So I'll just use my eraser. Is anyone still copying that? But you might automatically go to that spot. I know a lot of students do that to save time. They're like, I'm going to have to divide this, so I might as well just put a dot right here and flip everything over. That went here. This went down here. This went here, and this is that x to the n. There we go. I'll put bars around the whole thing. And this when it's less than 1. Almost done. Now it's just simplifying, true? Hey, I'm going to highlight. Where's the x? So it doesn't get lost. I think you'll love this section. We just got to be organized. I see it right there. So I just want to highlight it where it is so I don't lose track of it. There you are. There you are. Okay, I got you. I got you. I see where you are. Because it's all about the x. The problem's all about the x. Okay. You ready to start simplifying this stuff? Do I even have to worry about these negative 1s anymore? Do you want to just scratch them out? I mean, you can write this as negative 1 to the n times negative 1, but what's around it? Absolute value bars. What's the absolute value of negative 1 always going to be? 1. So does everyone just want to scratch these out right now? Okay, let's do it. You're gone. I'm just going to look at you, because the absolute value of negative 1 to an n plus 1 or negative 1 to the n, sure, I can write this as negative 1 to the n times negative 1, but we're saying all you're going to get is a negative 1 to the first power, and the absolute value of negative 1 is just what? 1. Cool. Leave that as is, because we're not expanding that, are we? Do not think you got to expand that. Leave that n plus 1 cubed. How can I rewrite that though?
X to the n times x.
And some of you do that right away, and that's okay too. Some of you you do 2 steps, 3 steps at once. That's x to the n times up x. How about that? 3 to the n times 3. So far, so good? You got the dot, you got this, you got 3 to the n. You got your n cubed right there. X to the n. We're staying organized, nothing's missing, right? All right. Let me highlight my x's again. Whoop. Whoop. There they are. All right, we'll cancel. X to the n's are gone. My mom? But that little x stayed, right? By the way, that will happen every time. 3 to the n's. They're gone. And this is what we got, right? Now this is how I'm going to write this next statement. Since the focus is at x with an absolute value bar around it, I'm going to put that in front of here, way out in front of the limit. Just because that's our focus. I'll put it way out in front of the limit as that approaches infinity. You go, can I do that? Yeah, does that have an n in it? Do you agree? So I'm going to write that right in front of this. So you and I can focus on this limit. All right, what are we left with? There's an n plus 1 cubed we pull that outside here, right, with bars. What else is in the denominator? A 3 and a n cubed. And we're trying to determine when this limit is less than a what? A 1. So I'm going to write that again. Cool, Jessica?
Can't you divide the n to the third? Can't you divide the n out of the parentheses 3 times?
I wish. The only way we could kind of look at this another way, Jessica, is if we expanded that thing. You know, like a m plus 1, then an m plus 1, then a... And we're like, oh, good golly. There's no need for that. Because we're just trying to get a limit. So we can either look at the Horace, or we can do L'Hopital's rule. If you're a L'Hopital rule fan, L'Hopital's rule, go ahead and do L'Hopital's rule on that limit, right? If you're like, I like to just look at the horizontal asymptote. Does anybody know the Horace? Because the powers are the same. It's going to be the coefficient, which is 1/3. Now, if you don't see that, you can do L'Hopital's rule, where you just take the derivative of the top, derivative of the bottom, you'll eventually get there. Anybody want to see L'Hopital's rule real quick to see that limit's going to be 1/3? Let's see. What's the derivative of n plus 1 cubed? 3 times 1 squared. What's the derivative of the bottom? 9n squared. So far, so good? Now, I still get infinity over infinity, so do the derivative again. L'Hopital's rule. Take the derivative of the top. What do you get? 6 n plus 1. What's the derivative of 18n. I still get infinity over infinity. So now, take the derivative of the top. I'm going to just show you that. And the derivative of the bottom. What's that derivative? I'm just going to keep doing L'Hopital's rule here. What's that derivative?
6 over 18.
Which is? Cool. So if you're a L'Hopital's rule fan, you don't look at that horizontal asymptote of these rational. You didn't recognize it was a rational expression. You can always do L'Hopital's rule to find those limits if you're a L'Hopital's rule fan. But there's no need to go expand that thing, right? That's why. Hey, but some of you might realize, oh, that's just 1/3 the horizontal asymptote of that rational expression. So, this is what I have now. I have an absolute value of x. I'll put it in yellow. What's this entire number right here? So I am going to substitute just a 1/3 there. This is all gone, but what's still over here on the right side? Less than 1. Let me put this down so we can see it. Less than 1. That's our math problem. And I'll rewrite it over here. Can I erase the L'Hopital's rule work? Yeah. So let me write this again. What are we left with?
Absolute value x.
Absolute value of x.
1/3.
A 1/3 and a left one. We're about to get the radius of convergence. To get it, you got to isolate this absolute value of x. That's all you got to do. So how do you get that 3 off that denominator? Down the right side. Multiply it, right? Hey, when I multiply, do I have to switch the direction? No, that's only when you multiply a negative number, right? I just hit. Now there it is. That's the radius of convergence. That number right there, and you'll see it. We just found the radius of convergence. It's a 3. You could write r equals 3. But I encourage you to draw a number line. I don't know if you'd find this in the textbook, but can we talk about these x values? Because we just found the values of x that make this converge. Can we draw this on a number line? Sure. Take off the bars. I can put a 3 here. What do I got to put on the other side?
-3.
Good job. You just solved the absolute value inequality. What's that look like on a number line? Just so we can look at these numbers. You just found all the values of x that make it converge. What's centered in the middle? 0. What's on this side? 3. And what's way over here? I'll even put tick marks. -1, -2, -3, 1, 3. And you're saying all the values in here for x will make this converge. Cool. But do you notice what I mean by, and I'll get your question wrong, Connor. Do you notice what I mean by radius? Like the radius of a circle, you go from the center what? Out. Let me say that again. Radius of a circle, you go from the center out. So if you go from the center out, what's the distance? 3. So maybe a better way to say this. Radius convergence. It's a radius of 3, and then I'll write this. Centered at x equal to 0. The book calls x a. you could say centered at a equals 0 or x equal to 0. We're just talking about, what values make that converge for that. So Connor, go ahead.
So you just divided out the 1/3, right?
That right there, what I did, oh yeah, you could think of it that way. Divide a 1/3 on both sides. That will work.
Okay.
So when you divide a 1/3 here, it becomes a 1. A 1 divided a 1/3 becomes a 3. What someone else suggested, and this is up to you, they said, why don't you multiply it through on both sides? Right now, that's what he said. Both of them work though.
If you multiply, would it be a third?
Look what would happen. So you multiply a 3 over here, then you multiply a 3 over here, and they would cancel.
Oh.
But what you said was fine. You said, I will divide 1/3 on both sides. That works too.
Okay.
And I'll go back to write it as is, but Connor, if you prefer that division of the 1/3 on both sides, that's totally fine.
Thank you.
All right, man.
X isn't always 0, right? It's just whatever's in the middle of your two.
That's right. And so this problem, this had an x here, centered at 0. That would be centered at 0. And my next problem, you'll notice it won't be centered at 0. And you go, what makes it not centered at 0? And you'll be able to tell. You could see it right away at the beginning of the problem.
Isn't it because of when you move whatever's there to, when you don't, I guess, normalize it?
That's right. That's exactly why.
So if you were to have like x minus 1, it would be centered.
You just answered the question. Mandy, does that make sense? He says, if that problem started with a, right here, like a, okay, that thing's going to be centered at 1. I can keep going. What was x minus? Centered at 3. Just if you want, anybody want to be able to spot it from the beginning. X minus 5, that would be centered at 5. Hey, a trick question. What if it's x plus 5? Centered at negative 5. But when it's just a x to the end, it's going to be centered at 0. Hey everyone, we got it. We found the radius convergence. You can just write your answers like this, r equals 3. That's what you're going to see when you look at Bob. Bob's back a book. When you look at Bob, it's going to go capital R equals 3. One more thing. We got to talk about this interval of convergence. Well, don't we have it? Yeah, but we should check the endpoints. Maybe we could put an equal sign here. Or maybe we could put an equal sign here. So we're going to check the endpoints just to make sure. It's not a big deal. Don't think it's like, oh gosh, more work to do. We're just going to do this. We're going to take that number, go to the original, plug it in for x, and see what happens. Just examine it. Then we'll come back, we'll plug in -3 into that original, look at it, see does that converge. Okay? So when we're now going to determine whether or not I can put in equals here and equals here, it's not a big deal. And when you've done, to me, you've done what? 98% of this problem. 98%. We just got 2% left. I'm just going to check what? That number and that number to see if we can put equals on. So you ready? You want to start with the 3? Let's go up there. Let's check endpoints. Check the endpoint, x equals 3. So what do? Plug in a what? And I need to just examine this. You get -1 on the end, and cubed. You got a 3 to the end, all over. Just examine it. You do not have to do the ratio test here. Just examine it and tell me your thoughts on this. Does anything cancel? The 3 to ends cancel, huh? Now, does everyone see what I did? I just simply plugged this 3 where? For x, right? Maybe I should color code. And again, this is not a big deal. You're just going to check these two numbers in the original series. All right, what cancels? Whoop, whoop. Now, tell me about that series. Would that converge? If it converges, we get to put an equal sign. So I want you to think about that. -1 to the n cubed. Start plugging in like gigantic numbers. Everyone, isn't that thing diverging? I mean, it's going to be plus and minus, and n cubed means it's sending towards what? Infinity. It's going to be infinitely large, and it's also changing pluses and minuses. So it diverges. You know, if you wanted to write something out here, you don't have to. But if you wanted to write, well, that would diverge by test for divergence, which it does. But we can't use 3. So I'll just put a sad face. 3 is no good. Can't include which number? X equals 3. If you want me to explain, let me say it again. Why did this happen? Why is this series divergent? This diverges by the test for divergence, the limit as n approaches infinity that is not existent. D.
Wouldn't that kind of follow because of the less than signs are less than or equal to, so they just exclude those values?
That's right. Very good. Hey, what's the other endpoint?
-3.
All right, well, let's check that. Check this endpoint. Now, when check endpoint, x equals negative. All right, let's play it out. Check the endpoint,
Same one.
x equals negative 3. So what would this series look like? I would have a n equals 1 to infinity, negative 1 to the n cubed, and then negative 1 to the n? Or negative 3 to the n, excuse me. Let me color code that. I'm plugging it in right there for x. And a 3 to the n. And then you and I are going to look to see how this plays out. And I'll move this so we can have more work. If I add this, I can draw in there and go. After that, x is less than 3. Means x is between 3 and negative 3. There we go. But we're just investigating whether or not we can put equal signs here. We already know we can't put an equal sign here, right? What about the negative 3? Now, anybody know how I can break that up? We gotta be able to break that up. I wanna break this up so I can cancel the 3 to the n's. Do you know how to do it?
-1 times 3.
I'm gonna do it. So when n equals 1 to infinity, leave that. Leave that. He says make it negative 1 to the n times 3 to the n. That's something you'll do often in the next, we're in section 11.8. 11.8 to 11.10. That's something you will do often. That you'll say, I can rewrite negative 3 to the nth as negative 1 to the n times 3 to the n. And that's just by the rules of exponents. Oh, Dave, go ahead, you had a question.
Never mind.
Oh, you good? Oh, cool. Hey, what cancels?
3.
All right, these are gone. Now, what's that times that? Bases are the same, you can add the exponents. So that would be negative 1 to the, what's n plus n? I'm okay with that. I'm using the rules of exponents. I can add, I get the same bases, add these up. But negative 1 to the 2n, hello. Won't that always be a 1? Try it out. Put a 1 in there. What do you get? Negative 1 squared. You put a 2 in there, you get negative 1 to the what? 4. This is always going to just be a 1, isn't it? So I'll rewrite this. But I think we all know that does not converge, does it? That's divergent. That's going towards infinity. Diverges, if you want to know why, by test for divergence. So when, after we spend all that time, thanks for bearing with me, we checked this other endpoint, we can't put equal signs. That's the answer. Some of you might eyeball it, you know, but you gotta put some scratch work down, write some, just to check it out, Dave.
So the checking the points is actually just to confirm or whether or not you're adding equals?
That's right, that's all it is.
Okay.
And I'm being honest, like, don't let it overwhelm you. I'm saying 98% of this problem was to seriously get this, everyone. You've accomplished a lot, right? That's the big deal. You got the radius. You know where it's centered. You got an idea of the numbers that make it work. Now you're just checking what? Can I include those? Can I just include those and put an equal sign in this? And we just discovered I'm not allowed to do it, am I? Sad face on both of these. I'm not allowed to use the negative 3, it doesn't work, and I'm not allowed to use the 3. So, hey, sorry, I can't put an equal sign there. That's the interval. Just so you know the answers, this is that interval of convergence. And what's the radius? 3, you don't have to put centered at 0, but I always write that, Amanda, just for clarity, so you can get an idea. Oh yeah, what radius means. Look, I go 3 that way, and I go 3 that way. Cool. And I wait till everyone's done copying, we'll do another one. But you got it. How about this section? Every time we do the ratio test, and it comes down to the end, then we'll just check those endpoints. Can I erase? Cool. All right, here's the next one. Hey, I wanted to make sure, pick a bunch of problems that really kind of reflect the homework practice problems. That one was like number 9. if you're curious. This one's also like number 9, but it's based off what Dave and Amanda are asking about. So all I'm going to do in this problem, everyone, is change little things. Maybe this one doesn't have a -1 to the end. Need the directions. We'll figure out the radius. All right, here you go. Power series. Does this start at 1? They either start at 1 or 0, you'll notice. They don't have to, they could even start at a 3 or something. But it's got an n squared. It's got an x minus 2 raised to the n over 4. Over 4 to the nth power. There's the power series. So they call this a power series. The C sub n is all that junk right there. That's the C sub n. So, oh, this x to the nth can be x minus or x plus a number. Cool. So hey, again, I'll highlight where this x is. There it is, but now it has a what? Yeah, so that's the key. So when you know you're gonna have the end, and like your, I'll call it the penultimate step. In your penultimate step to the problem, you're gonna have this written. You'll have something like this, and you'll be getting that limit, just like before. There'll be a limit n goes to infinity. There'll be a bunch of junk here, and you'll be writing this. That'll be the second to last step. You'll find that limit, and then Connor will just, should we multiply it on both sides or divide a number? That's what it boils down to. So that's what I mean, Amanda, or anybody, if you like, there's a lot of writing involved. If you can do 2 steps at once, that's actually okay. That's actually okay in terms of just write that limit as n approaches infinity and go to work. Are you ready to do the ratio test? Let's bust it out. Now that'll be the second to last step right there. There'll just be some stuff in there. We got to figure it out, right? All right. So when I'm looking at doing a ratio test, what's that become? Is it n squared plus 1 or n plus 1 squared? You all are awesome. How about this next part?
Would be x minus 2 to the n plus 1.
All over?
4 to the n plus 1.
Way to go. And up at the bars. Did I forget anything? This can happen. When I did so much writing, you're on a test. I did so much writing, I might have forgot something. So I have to divide this by a sub n, right? Okay. So this is where I'm going to put a bar here and put everything down here. But Lottie, if you want to save time, what are we going to do in the next step anyway? Put a dot and then flip it. So I'm going to do that. Put this bar here, dot it, flip it, that goes up there. Here comes the a sub n. Let's get it down here. If you want to highlight that x minus 2 again, you can. And we're determining when this limit is less than 1. Ratio test. That'll be our second to last step. Why? Because what happens here? N plus 1 squared. Do you have to FOIL that out? No. What's that? X minus 2 times up to the n times up. Cool. 4 to the n times up. 4. For the n, that's an n squared, and that's an x minus 2 to the n. I don't want to rush you, but is that okay how we got that thing simplified? Not slash time, slash it out. Slash away. The worst is when your eyes miss a simple number like that, because that 4 right there will really affect our limit. So don't be knocking that 4 out, right? What goes out? You're out. You're out. This is out. This is out. That one, just like we expected, guess who's hanging around? This 20x minus 2 with the bars on it. So I'm going to put this out in front of this. Just get it out of the way. That's our focus. We'll have that at the end, but now we're getting this limit. It's just a limit problem. I can take off the bars. Everything's positive. What do you have? 1/4 of n plus 1 squared over n squared. No need to expand that. You could do L'Hopital's rule or think of the Horace, because that's a rational expression. What's that limit? 1/4. That limit's 1/4 then. So now, you know what's neat? I said that's the second last step. You were right here now, and you just figured out that limit. This limit, right there, is 1/4. X minus 2 with bars on it times the 1/4 is less than 1. I'll go to you, Connor. It's up to you. Do you want to divide 1/4 or multiply 4? Either way you want to say it.
I like dividing.
So this is what he does. He goes, I divide 1/4 on both sides. Now if this had a 4 here, he would have divided a 4 on both sides. So he's thinking always division. That's a great way to roll with this. But when you divide a 1/4 from a 1, what happens? You get x minus 2 less than a 4. So I'll erase this, everyone. I know the radius already. The center is not 0 anymore. Where's the center? Yeah, x equal to 2. The book likes to call it a for some reason. If you want to write a equals 2, that's the center. Right, center 2. What's the radius? It's on the other side. What's the radius? 4. So will this always be the radius over here? Sure. I want you to see it. Let's see why. This will always be your radius. Centered at, pick the opposite sign. So centered at x equal to 2, a equal to 2, with a radius of 4. What would this look like on a number line? Well, we're going to look at the interval too. Less than 4 and greater than a negative 4 is going to be my next step. I don't want to write that yet. Someone help me take these bars off? I pull them off, what goes over here? Negative 4? Like in an intermediate algebra class, an absolute value inequality. Now solve for x in the middle. The highest it gets to is 6. What's negative 4 plus 2? Negative 2, good. And look at the number line. I like to just draw it out. All right, went to a negative 2, and then negative 1, 0, 1, 2, 3, 4, 5, and 6. And the center is where? Yeah, here's the center. And how far is it? Either way, the radius is what? The radius is centered at 2. So the back of the book would write this. R equals 4. But there's one last thing left to do. Think of it not as tedious. It's just you've done really 98% of this problem. Can we check those endpoints again? You know, it's like just checking them. Put the negative 2, put the 6 in there. And this time, I'll start with a 6. If I put a 6 in there, this time I don't have to write as much. We'll simplify it. Look what you get. I'm checking the endpoints. 6 minus 2 is a what? 40th, and I get that. I just want to make sure. Does everyone agree? Does that converge or diverge? It diverges. Sorry. Can't put an equal sign. Now, how about the x equal, what was the other endpoint? Let's try x equals negative. Then I'll have the summation of n squared times, now watch what happens here. What's negative 2 minus 2?
Negative 4.
Negative 4 to the nth. How can I rewrite negative 4 to the nth?
Negative 4n.
A negative 1 to the nth and a
4n.
40 nth, which will cancel at the bottom. Does that converge? That's a plus or minus infinity, right? Isn't that where that sequence is going? In terms of summing that up, that diverges by test for divergence. Does anyone see that? All these, the last 4 things, when we check the endpoints, diverge by test for divergence. The limit was not equal to 0 of the sequence. That sequence. Hey, so that's our answer. If you want to write, what's another way to write an interval of convergence? Does anyone like to put it in interval notation? Like this? Like I can call this my interval of convergence. My IOC. My interval of convergence. Do you like to put it in interval notation? You absolutely can. what does it mean if you got to put an equal sign there? You gotta do what? Close brackets. But you can leave it like this. So there's my interval of convergence. My radius is what? 4, but I always like to include where it's centered at. Where was this centered? At 2. So you're really talking about those numbers in there. You're the mathematician, the computer scientist, etc. You're going, the numbers that work for this are right there. All these in there work. Not only the integers, all real numbers inside that interval. Hey, so summary on that. The radius was 4, and the interval was -2 to 6. Hey, I want to do a couple more of these. You know the ones where you get a funny answer? Let's do one of those. And then I saw one. We should definitely at least do a problem where you at least get one of the endpoints to what? Converge. After this, you might think the endpoints never work. True? Sometimes they do. Juliet.
So if it works out like you plug in the values that you got, like -2 and 6, and then they end up converging when you plug them back into the original equation, does the interval of convergence change?
The only thing that changes is that symbol at the end, or the symbols right here. The only thing, and all you would do if it converged at 6, you'd get to put that.
So it doesn't change the interval?
Will not change the numbers at all.
Oh.
And that's why, Juliet, I want you to think of it as not such a big deal to you. You're like, man, I've got this problem really done. I've done 90, that's what I mean, 98% of it. I'm just checking, because there's so many numbers in here. You're just checking these, what? These extremes at the end to see, can I use those as well? I know, there's some institutions, you know what? They just want the radius. They're like, hey, don't even worry about checking the intervals. They just want to know what the radius is. Wow, let me check this. So I don't want you to think it's such a, don't let it be such a burden. Hey, cool. The key is getting that radius and where it's centered at. All right, here's the next one. Hey, just a couple more of these. We'll go on to the next section. Oh, it's got an x minus 1 in the end. There's not much here, though. There's no -1 in the end or anything. This started at 0. Sometimes they start at 0. Everyone, determine the radius of convergence. What test are we doing? Ratio test. You ready to roll this? Boom, boom, down goes a fade. What's that big going? X minus 1 to the n plus 1 all over n plus 1 with a factorial. I don't care how I wrote that. Now what are you putting underneath it? That exact expression, and I'll put the dot and flip it, Dave.
I was just gonna ask in the test, are we able to just skip that step?
Yes, yes. There are many people who agree with you. The only thing, 11.8, cool section. You notice, it's like, boy, there's a lot of writing. If I keep writing everything. And if you're a student, Dave, sometimes writing everything makes you make errors.
Right.
And you're able to say, in my brain, I can do 2, 3 things at once. Put this over here, I know how that will simplify, that's fine. You know, I'm going to put the dot and I'll flip it. What's on top? There's the ace of that. I'm doing this part. It's just, when you divide a fraction, you multiply the reciprocal. And limit when it's less than a what? So this is what Dave's talking about. What happens every time when we write this? This becomes what? See, this time I'm going to use my eraser. Has everyone got all that written down? I got it easy, I got the eraser. This means what? X minus 1 in the end times up. So we know it cancels there. These just what? This will go out here. That's that x minus 1. How do you simplify that? Do you remember? I like to go off to the side so everyone's okay with this. How do you simplify n factorial over n plus 1 factorial? Dave was mentioning this also, I believe. That he's saying, you know how that simplifies, don't you? So he can do that in his head. And that's what he means, because he can immediately just, I know how that simplifies. Factorials will be able to cancel. That would be like, just give me an example. That's an n, what would be next? N times n minus 1, keep going lower. What's this? N plus 1, what's 1 lower than n?
And
And what's lower than that? Cancel.
everything but
So everything cancels here. Everything, except for the, so catch my error. So I'm saying this right here is equal to n plus 1?
One.
Is 1 over n plus 1. See how, when you have factorial over factorial, you can always simplify it, or you can eliminate those factorials. Is everyone okay with that? The book would write this as, hey, that's n factorial over n plus 1 times n factorial. You can just, that's how they would write it. But I want you to be able to see it. It becomes just 1 over what? N plus 1. So in this right here, simplifies to 1 over n plus 1. Where's this going? Out in the front. That's our, I want it to be our key focal point at the end, right? There it is, sit out in front of the limit, doesn't have an n in it. What do you have here? Multiply that times limit, does n go to infinity of? Just this. So this becomes a very interesting problem. I know you know how to find that limit. I don't even think you have to do L'Hopital's rule. It's just what? 0. See the higher power at the bottom? So, can you help me think about this mathematically? What numbers make this converge? This is now a 0. And this is the first time we've gotten a 0 today. You and I are looking at this math statement. Whoops, I forgot to put that other bar on. This is what we're thinking about with these problems. Determine the radius of convergence. Determine the numbers of x that make it work. Determine the numbers of x that make this thing converge. So I'm trying to think out mathematically what x values make this a true statement. When the absolute value of x minus 1 times a 0 is less than 1. This has a very interesting answer when you get a 0 here. Because what's anything times 0? 0. So don't think the opposite. Don't say there's no solution. There are many solutions. Now, can I give you some examples? I'll use 10. If I put a 10 in here, is this a true statement?
Yes.
10 minus 1 is 9. What's 9 times 0? Is that less than 1? Okay, let me just pick another weird number, pi. Pi minus 1, great. It's some weird, funny, irrational number. You multiply 0, you get what? 0. So what are we saying here? If I get a 0 here, every time, 0 times something will always be what? So what the heck's our answer? It's not, it does not exist. It's the complete opposite. Our radius. Are we thinking all reals? For x? All real values? So here's our radius. What's the interval? How do you write that in an interval? And we can't check those endpoints, can we? But everyone see that? I want to make sure you know why. Anything times 0 will always be less than 1. Put that in your notes. So if you're wondering why we did this. Any values of x in the entire real number system, you multiply a 0 to it. You're going to get 0, which is what? Less than 1. My worry is, you notice what I'm not writing down right now. You know, if I just wrote this times this is 0, and then you might look at your notes and think, there's no answer. No, there's a bunch of answers. All values of x work. Now that's huge to a programmer. Who are the programmers? And so you're like, oh my gosh, this thing, I don't have to worry about what x has to be. It can be anything. X can be 1,000,000. And this series converges, right? Do you know what made it did? I think y'all noticed. The factorial being in the denominator. That carried a lot of weight to the math behind it. We know about factorials and how rapidly they explode. That's what made this work like that. Cool. I know if it was like 2 to the nth, it would have been a different story. If that was 3 to the nth, it would have been a different story. If it was an n factorial, look how it played out.
So it doesn't matter what the center is for these kinds of problems?
Oh,
Just be any-
what is the center? From negative infinity to positive. Let's pretend that's positive infinity. Let's go way over here, Katie. This is negative infinity. What is the center? What's the middle? What, 0? You could say centered at 0. But we're just thinking, hey, it's all real numbers. They said find the radius. So you know what our radius is? It's infinitely large, is what we're saying. It's infinitely large. You get the whole, it's all real numbers, but that's how we write the answer, and that's how we roll. All x values work. Right? Oh, I got you. The centered at 1 thing people were saying. Centered at 1. You could write that. But key in on, that's my radius. That's my interval. Because of what? What's making that do that? This is actually good. Because I want 0 times anything is less than 1. Any value here. Ooh, so that's an interesting one. Okay, one more. And then you're like representing functions of the power series. And when you got this down. Alright. And when this is like number 17. This is like number 17. That last one was like number 7. Just trying to make sure I hit pretty much the spectrum of the practice problems I put down. This has, okay, how about a 2 to the n? This has got a, I wanted to give you one that had like a plus in there. So I wanted to give you that. What if it's x plus 2? Amanda, do you remember where the radius, the center would be in that? There, yeah, it'd be centered at -2. And oh, this had a square root. So I want to at least give you one of those as well because I didn't want the square root to bug you. We're determining the values of x that make that series converge. We immediately go to the ratio, so the limits, and it goes to infinity. And watch, I bet you there's people in this room already, you're off to running with this. You're off and running, and you're doing 2 steps at once. But that's not every student. I also highly respect the student who goes, I read everything. And sometimes I need to get out a piece of paper, extra piece of paper, and that's fine too. That's 2 to the n plus 1. That's x plus 2 to the n plus 1. That's the square root of n plus 1. Hey, Connor, okay with that?
Yeah.
Oh, good. So, and then I'll just divide that a sub m, which means multiply the reciprocal. What goes down here? What goes up here? We got. And this is when this limit is always less than 1. Always less than 1. Always less than 1. Now I'm going to do the eraser thing again. So everyone copies that. And you're going to help me simplify, cancel things out. I got it easy though. I get this big green board. I could just erase things. Let's go away. To save some writing. All right, I'll start with that. How can I write that? 2 to the n times up 2. I bet there's people in here who do that amazingly. That's good. How can I write that? X plus 2 to the n times up
X plus 2.
x plus 2. That happens every time. We got it. Whoops. And now it's time. Oh, what else cancels? Thank you. 2 to the n. So don't forget about that 2. The square root. This is coming out here. With bars. With bars. Now I got a limit. Because n approaches infinity. I don't have to put these bars here anymore though, because n is positive. It started at 1. So if those bars get in your way, don't let those bug you. And if you get a -1 to the n, it just turns it into 1. I didn't miss anything with my eyes, right? I'm looking over. Got that. Got the 2, that was important. And we're determining when this limit is less than 1. So, I hope you know this limit. Even though it has radicals, aren't those, hide that. You see what's going on? Coefficient, what is it? You are good. That is awesome. You just said that limit's 2. I mean, you could have done L'Hopital's rule and stuff, did the derivative, but that can be a little messy. So that limit's 2. So this is interesting. This is the first time today we didn't get like the fraction. Remember we kept getting 1/2 or 1/3 or 1/4? That's a 2. So now, Connor, what would you do?
Still divide it.
Because that's what he does. He goes, divide 2 on both sides. But the key is, you're a step away. We're going to find that radius. You find the radius key every time when you get this thing isolated. That's the, what's the center again? X equals -2. The radius that you're talking about, that we're trying to find, will always come out to be this number on the right once you got this wiped out. Now how do you get that 2 off there? Connor said divide at 2 on both sides. So now a 1 divided 2 is what? Guess what the radius is? That's your radius. Here, the radius for this problem, 1/2. Back of book would say r equals 1/2. The book doesn't do this, I like to write this. What's the center? This is really a Professor Messenger. It's centered where? Centered at, so that means you don't have to put the center part. I just like to talk like that, so it really gives you an idea of the number line. Radius 1/2, where's your half radius? That's what I mean. So it's centered at x equal to what? -2, isn't it? Well, let's play this out. Let's look at the interval. Hey, Katie, okay with that? All right, and we got that answer. Now, how do I keep the bars off? What goes over here? So what is x between?
-2.5 and -1.
So, good job. 1/2 minus 2 is a -1.5. What's that, -1.5?
-3/2.
All right. And then everyone subtracted 2 from a -1/2.
-5/2.
That's -2.5, -5. 98% of the problem complete. We're just going to check that number, Juliet, and that number to see if you and I can put a simple equal on either side. We haven't been able to do it yet, though. Right? Well, let's check it. All right, so I'm going to check the endpoints. I can do it here. I got enough room right here. I'm going to check the endpoints. All right, what's one of the endpoints? I'll check. How about that -5x? Now let's plug that in. I get to the nth times, what's -5 plus a 2?
-1/2.
-1/2. Tnth over
Root n.
let's square it out.
Yep.
Well, that looks confusing to me, so I'm going to try to rewrite that. I'm checking my endpoint here, so I'm going to rewrite this. Can I put that 2 to the nth in the denominator and leave the -1 to the nth in the numerator? That's what I'll do. Because I think something cancels. Watch this. 2 to the nth there. Leave the -1 to the nth up here, and right next to that square event, I'll put that 2 to the nth down in the denominator. See how this was upstairs, and I put that downstairs with that. So you could see what cancels. What cancels. And look at this series carefully. This is the first time this has happened today. Think of all your tests that we did in the previous week. Think of everything. Does anybody know whether or not that converges? Does that series right there converge now? I'm checking this endpoint, -5x. I get this. Does that series converge? What would be a good test with a -1 to the n? That's the hint. Alternating series test. Everyone, look at the b sub n. What's going on with the 1 over the squared of n there? That's approaching what? 0. This baby converges by AST. We get to, Juliet, put an equal sign there. This gets a smiley. This works. This works. This converges by AST. Everything else today was just divergent at the endpoints. Converges by AST. Look at that. Hey, this means I'm so happy I finally get to do what? I get to go like that. Cool. What's the other endpoint? I don't know if I can get both of them though. Here, maybe. Let's try the other one. What is it? I don't know if we're gonna be so lucky. What if you put a -3/2 in there?
1/2.
Oh boy. I don't think that's gonna be so nice then. 1/2 to the n?
Yep.
Uh-oh, everyone. I'll put the 2 to the nth in the bottom. What's gonna cancel? Let me rewrite this so you can see how it cancels. That means that, right? You know what a positive 1 to the nth is always? Just 1, so ignore that, but these do what? What do you think about that series? I don't care, you can think of any test. We can't use the alternating series test. Man, you are fast. Did you know how fast they know they got the P series? Less than 1 diverges. Hey, cool. And when they're saying that's a P series, where the power is less than what? It's equal to a half, right? And then the 1/2 power, which is less than 1, that means it diverges. We can't equal that. There's your answer. That's the interval. That's a radius. If you want to put this in interval notation, how can I write that in interval notation? You can just do bracket, -5/2 and. Hey, but kind of cool. This is the first time we got the what? Got to put the closed bracket on one end. Finally! Don't let that bug you though. It's really just checking the endpoints. Don't let it be such a drag. Because what I'm saying is, look what you did. You figured out all the values of x that work. There's a lot of numbers in there. There's an infinite amount of values in that interval. You're just checking that endpoint. Okay. Hey, the last stuff we'll do today is representing a function as a power series. Oh, go ahead, Dave.
I was, for the first one where you said it converges, can you tell me exactly how it's converging again?
I sure will. So it's one of our old tests. One of the tests from the previous sections. When I got down here, these canceled. I got a -1 to the n over square root of n. So I immediately thought of the alternating series test. That's what I thought of. And for the alternating series test, the term's got to decrease. 1 over square root of n, that decreases. And number 2, the limit of v sub n, that'd be the 1 over square root of n, has to equal 0. And the limit of that is equal to 0. So I go converges by alternating series test. Every one of the other ones, except for this one, we were able to say, when we looked at the endpoint, diverge by test for divergence. This was the first one though where I couldn't use test for divergence. Dave, I think it was Dave suggested, well, let's look at it as a p-series, because it didn't have the -1 to the n. And the p-value right there is a half less than 1. That's why this thing is actually divergent. Okay, thank you. You bet. All right, I'll write all this, get this out of the way. Function as power series.